So as he said, this one's going to be on regional hydration near the Viper landing site, a remote sensing view. So the search for water is on. I'm pretty sure we all knew that though. But what we don't understand is what the origin, distribution, abundance, and behavior of that water is on the lunar surface. And one really exciting and upcoming mission that's going to make a lot of headway on that is the NASA Viper mission. So Viper is going to land near the lunar South Pole in the Nobile region in late 2024. And we're going to do a 100-day surface mission in search for water ice and characterizing the lunar environment down there. Viper is going to cover about 90 square kilometers, and I hope I got that number right. But what I'm really interested in doing for this project specifically is understanding how much water and hydration that Viper is going to see and extend the Viper measurements from beyond its projected traverse or the actual traverse that it takes. And so we're going to do this by using data from 2 Earth-based observatories, and I'll introduce those soon. But what's really important about this is that the Earth-based observatories are going to extend the reach of Viper to a little bit broader context of the lunar surface. But Viper is also going to provide ground truth measurements for our 3-micron hydration observations from remote sensing view. So as I said, we're going to use 2 Earth-based telescopes. The first one I'm going to talk about is the NASA Infrared Telescope Facility on Mauna Kea in Hawaii. So the IRTF SPECS instrument is a high-resolution cross-disperse spectrometer that provides 1 to 2 kilometer spatial resolution at the center of the moon. And this instrument covers the entire 3-micron total water band. Now, when I say total water, what I mean is hydroxyl plus molecular water, because at 3 microns, we can't distinguish between the 2 of them. And so we're not sure which of the molecules is actually present or in how much ratio they have. So what we're going to do with the NASA IRTF is we're going to look at the Viper region and understand how the ground truth measurements from Viper correlate to our remote sensing observations. And once we do that ground truth, we'll take IRTF and extend Viper's reach to a broader context. The other observatory that we're going to use is the Stratospheric Observatory for Infrared Astronomy, SOFIA. SOFIA is unique because it was the only observatory capable of measuring the 6-micron HOH bend of molecular water without any confusion from hydroxyl. Now, this 6-micron band is strictly due to molecular water, which is important for understanding how water and hydroxyl behave separately and not together like we see at 3 microns. And SOFIA was unique because at 6 microns, you can't make these measurements from a ground-based observatory because Earth's atmospheric water completely drowns out the signal. SOFIA operated above 99% of the Earth's atmosphere because it was an airborne telescope, allowing us to make these measurements for the first time on the lunar surface and search for molecular water on the sunlit portion. So this 6-micron spectral range is also unique because there are no current or planned spacecraft capable of making these observations. So while SOFIA is grounded, we have a ton of data that's going to make headway on the distribution, abundance, and characterization of the behavior of molecular water. Okay, so these are the observations that we're working with of the Viper high latitude region. So we have one observation so far with the IRTF at 3 microns outlined in, do I have a pointer? No. Outlined by the red box. Then we have 2 observations performed by SOFIA, and I have flight IDs just to help separate the 2 different observations. So 912 covering that blue box and 826 covering the purple box. And the first thing you might notice is that they don't cover the Viper region, or not all 3 cover the Viper region. This is because when SOFIA was conducting these observations, we didn't actually know where Viper was going to land. We knew it was going to land somewhere in the South Polar area. And so we did our best to cover what we could to cover the Viper region before we really knew where it was. And you'll also notice that the IRTF doesn't extend down there. So with the IRTF, we have more observations at the South Pole or of the southern hemisphere that we can dig into and try and find observations of the Viper site. If we don't find those, we can conduct more observations with the IRTF to get the Viper measurements. All right. So here are the radiance maps, and these maps are just to provide some context of where we're looking at the South Pole. So in left two are Sophia observations, and I've circled the Moritus crater, which is a pretty prominent crater next to one of the biggest craters that you can see by eye, the Clavius crater. Looks like part of my map isn't showing up. Well, the map that's supposed to be on the right side is of the IRTF, and I'm not sure why it's not there, but the red circle is supposed to be showing you where the Moritus crater and how IRTF and Sophia are overlapping. So this is just to give you spatial context of what these maps look like for the water maps. And unfortunately, IRTF is still not showing up. So what we see in the water maps, though, is there's a ton to look at, and you could probably spend all day looking at these and picking out small features of showing the abundance of molecular water or total water if the IRTF map showed up. But I'm going to focus on two locations, the Moritus crater circled in red and the Viper site that has a yellow star. When we look at Moritus crater, the first thing you're probably going to notice is that the central peak looks dry. It's actually dry in the IRTF observations as well. This is really unique and interesting observation because it might say something about internal water in the lunar from the moon. But that's not the point of this talk. We're actually going to focus next to the central peak on the surface or on the floor of Moritus crater and look at the abundances on the floor between 6 microns and 3 microns, so hydroxyl versus molecular water, and understand if there's any diurnal variations. We're also going to do the same thing for the Viper landing site. And while we only observed the Viper landing site in Sophia one time, we got very close to it in the 912 observations. And so basically, if you look at the lower right-hand corner of the 912, I selected a spot down there to be close and representative to the Viper landing site. Okay. So here's just some statistics that you can look at, and wow. Oh, okay. It looks very messed up on these plots for some reason. What you're supposed to be seeing is where the labels are where the actual points are. Don't pay attention to the points on the plot. The 6 micron and okay, let's see. Let's just pay attention to the table instead. So what you would have seen is that for the Moritus crater floor region, we would have had abundances for 3 and 6 micron total water and molecular water that are roughly the same. They're within 1 sigma of each other. And so that at 10 a.m. for Moritus crater, what that indicates is that all the water or all of the 3 micron band is seeing is completely molecular water and not due to hydroxyl. This is a very interesting result. When we extend that further and look at the 6 micron diurnal variation, we go from 10 to 12 p.m. We see that there is a decrease in molecular water on the crater floor of Moritus. And that's really interesting because that says that the water is migrating around the surface with temperature or a lunar time of day. Now, if we're going to look at the Viper landing site, we see a very similar trend where from 6 microns at noon to 6 microns at 3 p.m., we see another diurnal variation with decreasing water with temperature and time. So this is very interesting. This says that the water molecule is responsible for the 3 micron band solely and I'm going to caveat that with, that's one measurement at one lunar time of day at one spot. And we see a diurnal variation both at Moritus and at the Viper site. So when we wanted to look into this a little bit further and understand what that means, we are actually seeing a latitudinal variation with over 6 different Sophia flights of molecular water. And then if we look at the diurnal variation, we see a diurnal variation or a temperature variation that is half the strength of the latitudinal variation. So this is very interesting results for us. Our observations are in agreement with previous M-cube and IRTF observations of the latitudinal trend and the diurnal variations. So just some thoughts to think about and future work. Most of the 3 micron band appears to be made up of molecular water at that one point, at one time of day, and one measurement. The Viper landing site showed a large variation in molecular water with lunar time of day. So we believe that the NERVIS instrument having about 100 ppm sensitivity should be able to measure these diurnal variations with a stronger peak at 3 microns during cooler times. And some future work that we really need to do to understand these bands is lab measurements of 3 and 6 micron bands together, to better estimate the abundances and understand how the bands are varying together. Thank you.